It's our pleasure to have Dr. Seth Koren from University of Notre with us. And today he will talk to us about generalized global symmetries and non-perturbative quantum flavodynamics.
Great, thanks very much. Thank you for having me. This is actually my first time in Texas. So in a way, I'm glad to be here for the full 100-degree heat. And I'm excited to tell you about this work, this program I've been pursuing the last few years to take some technology, some concepts from formal field theory and really apply it to learn new particle physics. I'll be talking mostly about these papers with my fantastic collaborators, Sungwoo Hong, who's another particle physicist, and many of you may know, and Clay Cordova and Kantaro Omori, who are more on the formal field theory side. So just a brief outline, I want to give you some picture about these formal developments, telling us that there are these novel, subtle notions of symmetries in quantum field theories that we care about, but go through it at a basic level before actually getting into new models of particle physics that we've been able to construct using that. I should say, please do ask questions and stop me. I'd like for people to follow along as much as possible. So let me begin with some very general motivation. Usually these days as particle physicists, we're doing perturbative quantum field theory, right? You expand around some vacuum states, you look at S-matrix scattering of Fock-based states. That's all fantastic, but it really can be the case that sometimes there are configurations which are very far away in field space that actually do matter and have important physical effects. And this is often when there's a notion of topology around. Let me just remind you of some couple basic notions thereof that come up in very simple theories. If I just have a real scalar that spontaneously breaks a Z2 symmetry, then the vacuum manifold consists of these two disconnected points. You can classify that with some sort of topological number, a homotopy group. And that means that actually in these theories, there are new, when you go to the vacuum, there are non-perturbative objects called domain walls, which can appear in, say, the early universe and affect cosmology that separate places in space-time where the scalar is in one vacuum or another. This is an extremely simple example that probably you've heard about before. If you let me just bend your mind slightly further, if you haven't thought about just a complex scalar that spontaneously breaks a U1 symmetry. This is an even richer sort of scenario. Now the vacuum manifold, the vacuum states form a full circle, and the vacuum manifold isn't disconnected in the sense that it was in this case, but in fact, there's a higher notion of disconnectedness classified by, again, a homotopy group, which leads to the appearance of non-perturbative objects made out of these quantum fields known as cosmic strings, around which the phase of the scalar rotates. Which again can appear in not just both of these, not just these very simple theories, but also in realistic theories of the early universe. Many grand unified theories have one or the other or both of these sorts of topological defects in them. And these are some fundamental extended objects that appear in both simple and realistic theories of high energy physics. Right, so that's great. Now, we know, of course, as fundamental physicists, that symmetries are always very important, but usually when you learn quantum field theory, or when you're practicing quantum field theory, you think about symmetries by writing down the Lagrangian data of your theory and considering transformations of local operators, right? But as I've just reminded you, often theories that we care about have these extended operators in them. So it's a natural question to ask whether there is a notion of global symmetry that can be applied to these extended operators as well. And the answer, as we've learned over the past decade, is yes. That's this framework of generalized global symmetries. And the most basic, in some sense, notion thereof is of what's called a higher form symmetry. In this expanded framework, the familiar symmetries which act on local operators are known as zero form symmetries. They act on zero-dimensional point operators. And as you know, such global symmetries have a conserved current. Now, there are indeed, whenever we have higher dimensional operators, extended operators, there can be notions of higher form symmetries. Actually, the case that's
Good morning.
most today is of line operators, just the Wilson or 'Twight lines, which you may remember from
Thank you.
about gauge theory. Well, if someone's online, maybe they can mute themselves. Let me remind you that a Wilson or 'Twight line you can think of as inserting an infinitely heavy world line of some massive charged, electrically or magnetically charged particle. And these operators measure sort of the response of the system to that. And these sorts of operators can have a notion of one form symmetry. They're one-dimensional operators. And since it's extended operators, these also have a conserved current, but in this case, it's a conserved current with two indices. Slightly different. Now, before I go on, let me just briefly, already at this level, try to give you a brief picture of why you should think this is quite interesting as a particle physicist by briefly thinking about explicitly breaking these symmetries. Now, for a familiar zero form symmetry, the charged operators are local operators. And so you can explicitly break this symmetry by adding a charged operator to Lagrangian. This is very familiar. If I add, say, a Majorana mass for neutrinos, I explicitly break zero form global lepton number symmetry. Yes. However, I've just told you about these higher form symmetries, and the charged objects in these cases are extended operators. These aren't the sort of thing that can go into Lagrangian. And indeed, there's no deformation you can do of the Lagrangian that will break these symmetries. These sorts of symmetries only get explicitly broken when you go to higher energies and you see new dynamical degrees of freedom that appear, in a sense that I'm going to make explicit on the next couple slides in a simple example. Maybe I should briefly pause if there are any questions here.
So, you get globals.
That's right.
So when you bring those new operators, does that mean you bring gravity into this picture? Because gravity usually breaks these globals.
Yeah, quantum gravity is believed to break all global symmetries. Everything I will talk about today will be in the limit where M Planck is infinity.
Similar gravitation.
Yeah, that's right. But indeed, there is a very rich study that has been going on the last years of how theories like string theory break all of these global symmetries, and that's led to lots of fascinating discoveries of interesting sort of defects and non-perturbative objects that string theory has to have in order to break these symmetries. But I won't be talking about any of that. Yes.
So on the slide, one or two slides ago, when you motivated the presence of domain walls.
Yeah.
That to me feels like an object that forms when a symmetry breaks. But now you're motivating that a domain wall or cosmic string, et cetera, are a representation of this higher form symmetry. Is the domain wall in its existence a manifestation of the symmetry or the breaking of that global symmetry?
Yeah, good. This is going to become clear in the next couple slides. In fact, you're right that these topological defects are often associated with breaking either global or gauge symmetries. Normally, gauge like zero form symmetries, familiar symmetries that we know. Indeed, the dynamical objects, when we see them, will actually break these higher form symmetries. That's what I'm sort of getting at here. So actually, the cosmic string object breaks a two-form symmetry. But that would be hopefully made clearer on the next couple of slides when I'm going to talk about a little one-form symmetry more and the analogy. But you can ask me again if the analogy isn't clear. Good. Okay, so yeah, let me make this a bit more explicit by thinking about a very familiar, well-loved theory of particle physics, which in fact has some rich spectrum of generalized symmetries, and that's just pure electromagnetism. So let me remind you of Gauss's law, as we all learned in undergrad. You can draw some two-dimensional surface around, anywhere to some two-dimensional surface and integrate the electric field over that surface. And this Gaussian surface is topological. doesn't matter what size or shape you make the surface, and so it must compute some sort of invariant charge, topological invariant, right? That's what you learned in Gauss's law. But you might have always been a little bit confused about exactly what sort of charge you're computing here, right? The notion of a global charge that you learn about in quantum field theory is a Notre charge, okay? But a Notre charge, Notre instructs you to integrate over all of space at a given time, a three-dimensional manifold. Gauss is not instructing you to do that. So actually, what sort of charge is it that Gauss is constructing here? Well, we can understand this a bit more clearly by thinking about generalized global symmetries. And in fact, pure electromagnetism has a one-form electric global symmetry, which is just, you can see just by looking at the photon equation of motion, which tells you that in fact, the field strength itself is such a conserved two-index tensor. That is indeed the current of this electric one-form symmetry. As I just told you, with a two-index tensor, so one-form symmetry, the charged object is some one-dimensional operator. And indeed, anytime actually you were using Gauss's law, what was really going on is that you were considering a heavy Wilson line somewhere in space, and that point is just where it intersects that time slice. Here I have this more covariant picture, and you can write down Gauss's law in a more covariant way. And also, where you're integrating really the current over this two-dimensional surface. And that also makes it clear that really there is a full 3+1 dimensional topological invariance here. What you're computing is in some sense the linking of this Gaussian surface with the world line. And so it doesn't matter, you can deform your Gaussian surface in space and also in time. And this invariant quantity that you compute is actually invariant under all of those topological deformations fully. And so, actually, the answer is that Gauss's law does compute a sort of Notre charge. But it's a Notre charge not for a familiar zero-form symmetry, but for this one-form global symmetry. Okay? And that explains the difference in dimensionality as well. Okay. Now, I was clear to say here that I was working in pure electromagnetism, and the reason, oops, have I? Okay. The reason is that this electric one-form symmetry, can I get rid of that? This electric one-form symmetry is an emergent symmetry in the low energy theory of the real world at distances much longer than the electron Compton radius. And a very quick, easy way to see that is in pure electromagnetism, the only Wilson loops, gauge invariant Wilson loops you can draw are infinite world lines or closed loops, right? But once I have access to the electron field, then these Wilson lines can end. I can write a gauge invariant Wilson line operator that goes from, say, an electron field to a positron field. And then there's no chance that Gauss's law could compute something, a topological invariant. Gauss's law must break because I could deform this Gaussian surface straight off of my Wilson line. There's no chance that there could be something topological that Gauss's law computes anymore. And indeed, Gauss's law really breaks when you go above the mass of the electron. What you read, the analogous words you'd read in Peskin and Schroeder is that if you probe some heavy charge, do some scattering at high energies, eventually you see a cloud of virtual electron-positron pairs that start to screen the charge at energies above the mass of the electron. And indeed, it really is a symmetry associated with whether or not that screening takes place. Good. Okay, I'll mention parenthetically, it may be because of some interesting features of the standard model that there's a discrete sort of one-form symmetry that remains at masses above the electron mass. There's something we can test it at the LHC. It gives us non-perturbative information about the standard model related to grand unified theories. You should ask me about it later. But anyway, that's not the main point. Okay, and you should also think dually, as you know, your intuition might tell you, from electric magnetic duality, there are all of these dual notions of in pure electromagnetism, a magnetic one-form symmetry, which you might think about. Likewise, you could have a magnetic form of Gauss's law in the low energy theory. And again, now when I go to even higher energies and I see dynamical magnetic monopoles for electromagnetism, this magnetic one-form symmetry will also be broken. Good. Good. And so this is, Kevin, to answer your question, this is the sense also in which you should think that in the low energy theory, you have these two-dimensional cosmic string worldsheet operators, just like the Wilson lines. And actually, when you go to high energies and you see the cosmic strings themselves, those break the two-form symmetry, just like the electron breaks the one-form symmetry here. Okay. Good. Maybe another point where I should ask for if there are some questions before I remind you about some other gauge theory. Good. Okay. So some other gauge theory we learned that I just want to quickly remind you of is that sometimes in theories that we care about, you can have in the classical theory a good global symmetry, a zero form symmetry that I'll call, for example, U1x. But it can end up, especially if you have a chiral gauge theory like the Standard Model, that these symmetries in the quantum theory are anomalous. They have a mixed anomaly with the gauge group that can be classified as weakly coupled with these triangle diagrams. And that means that the classical current conservation of X actually is modified in the quantum theory to have this FF tilde term on the right-hand side. The anomaly is computed by these triangle diagrams. Great. Now, okay, so U1x is at least formally violated here, but actually, how do you see that this symmetry gets violated? What sort of field configurations can turn on this FF tilde term and actually lead to some violation of this X quantum number? Well, you may recognize that this FF tilde term is in fact a boundary term in the gauge theory that is nothing other than counting the number of times that the gauge field sort of winds around Euclidean infinity. It's a topological invariant of the field configuration, some non-trivial gauge field configuration, which we call field configurations which non-vanishing such term are called instantons in gauge theory, to remind you. And actually, even more so, how do we actually see this violation in the low energy theory in terms of what the Lagrangian does, the dynamics of local operators? Well, around 50 years ago, some remarkable work of Notre showed us that at low energies, you can think of what you should think of is that these instantons generate what we call Hooft vertices. I'll draw it sort of schematically like this, which are local interactions among all of the charged fermions, and which really concretely violate this X quantum number by the appropriate amount dictated by that anomaly coefficient. I can the details of this won't be necessary at all, but we can also talk about it more offline. Good. Any questions before I? Perfect. Great. So I was just telling you that instantons are the field configurations which can really turn on this symmetry violation. But in fact, for a long time, particle physicists, field theorists have been a little bit confused that there are some times when they don't. And the prototypical example of this is the case of a U1 gauge theory. And U1 as a group, it turns out, does not have enough internal richness measured by a topological quantum number, a homotopy group, does not have enough internal richness to non-trivially wrap the Euclidean, the boundary of Euclidean space, which means that there are actually no abelian instantons in R4. That is, in any photon field configuration, if you integrate it over R4, you'll find that this vanishes identically. So this is a little confusing because we have a scenario where formally the current conservation has been violated, but actually it seems like in our theory there's nothing that really implements that violation. So the old lesson that people took from this is, okay, X here is anomalous, but actually there are no instantons, so the S matrix will continue to preserve X, and so we can just ignore this anomaly. That's great, one fewer thing for us to worry about. And that's not, in a sense, wrong, but in fact, there's a better lesson for us to learn here. And I'll say, really, we should have been always quite confused by that scenario. Because as effective field theorists, I think you should think whenever you compute a zero, there must be some sort of symmetry that has dictated that some quantity has vanished. And so it seemed like this was some severe sort of violation of naturalness philosophy. And so you could have suspected that maybe there must be some sort of subtle symmetry that remains and is what's responsible for demanding X conservation in the S matrix. And you could have gotten a hint, if these words don't mean anything to you, that's fine, but you could have gotten a hint from this partially understood fact for a long time that actually, even in the U1 theory, there is a place where you can find this anomalous symmetry being violated, and that is whenever you have magnetic monopoles around. That's this famous Rubikov effect, which if you haven't read about, you really should, because it's amazing, and we're still trying to understand deeply what exactly is going on there. But you might have gotten a hint that somehow magnetic monopoles should be involved in what's going on here. And indeed, in the past few years, we have learned from this program of generalized global symmetries that what happens in this scenario is the symmetry X is not fully broken, but is converted into a subtler type of symmetry, which is known as a non-invertible symmetry. And it must now act, the only sort of symmetry that you can define that remains, now acts both on the local fields that you thought your X symmetry acted on to begin with, but also, in fact, on the magnetic monopoles, on the Toft lines, world lines of magnetic monopoles in your theory, roughly by giving them a small ionic charge, turning on a small electric charge for these magnetic monopoles. And so, okay, it's great to understand that there actually is a symmetry here. But I assert to you, this is amazing. Let me emphasize what we've found here. We have a symmetry which acts on local operators, and so directly constrains the operators in the Lagrangian, the dynamics of the theory. But since it must also act on these extended operators, it must break when the magnetic one-form symmetry is broken. It must break when there are dynamical magnetic monopoles around. And so you learn from an infrared symmetry analysis that whenever in the UV magnetic monopoles are introduced of the right sort, at least, if there were some operators that were protected only by this non-invertible symmetry, they must be generated at that stage. That's really amazing and gives us some concrete insight into model building. That is a bit of a grandiose slide, but indeed, this is some concrete new information about the naturalness strategy that we are gaining here. We learned that if you find in your infrared theory a spurion for a non-invertible symmetry, then you learn that that operator can be generated by non-perturbative gauge theory effects in an ultraviolet theory. I think really this is information which, as an effective field theorist, you would think you could not have access to in the low energy theory, right? You could mumble words about decoupling theorems, right? Some question like what operators could be generated by UV instantons is just a question that you don't think you can answer in the infrared. But indeed, if you understand what we're understanding from generalized symmetries is if you have information from extended operators as well, there really is more information that you can get out of the infrared theory. And so this is more powerful than just technical naturalness, which just tells you if there is some mechanism that makes an operator, a coefficient of an operator small in the UV, then it's protected down into the infrared. It stays small. This is more powerful because in fact, technical naturalness doesn't give you any hint even of what that UV mechanism could be. And here we're learning from an infrared symmetry analysis about what sort of mechanism some non-perturbative gauge theory effects could actually produce that small number. And so the examples I'm going to go over in the rest of the talk are cases where we've used exactly this logic to find a Dirac natural theory producing either exponentially small Dirac neutrino masses or automatically as beta bar equals 0, the strong CP problem. Good. Let me go. I'll go where I can just emphasize more concretely what the model building strategy is. If we find good. Eventually the theories that we construct, you're going to have some UV gauge group G, and it's going to be spontaneously broken down to a gauge group H. And of course, we're always as particle physicists, low energy effective field theorists, we only have access to the infrared gauge theory. And we want to understand what sort of information we can gain from the infrared theory. And so the scenario is, if we have a classical global symmetry that protects an operator we care about, and this symmetry has an anomaly with the gauge group, but some values of the instanton charge that it can have on a general manifold, say, are not actually realized on R4, then what we learn by finding X is actually a non-invertible symmetry is that this operator can be generated by instantons in a UV theory that introduces the right sorts of models. Yo, please.
The global symmetry has nothing to do with the gauge symmetry, right, to begin with. Or does the gauge symmetry give rise to this?
Well, they're related by the fact that the global symmetry has a mixed anomaly with the gauge symmetry.
So that means it does not originate from the gauge symmetry.
No,
So there is no gauge symmetry breaking and giving rise to these globals.
That's right. That's right. Yeah. I mean, you could think about a further UV theory.
Anomaly terms which is connected.
That's right. That's right. Exactly. Great. Any further questions? Now I actually get to normal particle physics, more or less normal particle physics. Great. So let me remind you, we have the standard model. We should say more often just how amazing this is. We know a theory that describes us and everything we interact with on a daily basis down to distances of 10 to the minus 19 meters, incredibly accurately, with only a couple dozen free parameters. That's really amazing. We can all pat ourselves on the back. But of course, we know it's not complete. We have more things we need to discover. And a simple way to go beyond the standard model is to gauge some of the approximate symmetries of the standard model. This is very familiar from, for example, grand unification, right? The reason that SU5 grand unification works is that the standard model fermions already have an approximate SU5 global symmetry. And what you do in SU5 grand unification is you upgrade that to a gauge symmetry to begin with that's then spontaneously broken. I'm in this talk going to instead go in the sort of horizontal direction and think about flavorful symmetries that we can upgrade to gauge symmetries. And in fact, I won't talk about it, but there is some further generalized symmetry structure that the flavor symmetries actually partake in. It won't be a feature of what I talk about now. Okay, so let me remind you, once I turn on the standard model Yukawa's, most of that U3 to the 5th symmetry is broken. Classically, we have in the quark sector baryon number, and in the lepton sector, because neutrinos are massless in the standard model, we have 3 different lepton number symmetries, 1 for each generation. And there are these mixed anomalies with the standard model gauge groups that we have to care about. So once you care about that, once you include those effects and think about which symmetries are actually remain in the quantum theory, you have baryon minus lepton number, which gets a lot of attention, but also, and you guys are probably more familiar with it here than most places I go, these lepton family difference symmetries, and it's natural to think about gauging them. And indeed, what I'm going to do, this is this paper in particular, what I'm going to do is to gauge L mu minus L tau, and as you probably all know, there's tons of phenomenological motivation to do this for the spectrum of neutrino masses mixing, or G minus 2 of the muon, or the anomalies, or what have you. But so I note when we gauge L mu minus L tau, then there is in fact, a new sort of mixed anomaly to care about. And in fact, the other lepton family difference symmetry, Le minus L mu, has exactly just such an anomaly. Okay, so this is exactly the sort of scenario we are interested in. Le minus L mu is classically conserved, but in the quantum theory, there is this FF tilde term for L mu minus L tau. But since that's just a U1, you can't actually have those instantons. And so indeed, this Le minus L mu is turned into a non-invertible symmetry in the L mu minus L tau theory. Okay, and in particular, the important part to focus on is a Z3 subgroup of Le minus L mu, which is actually generation independent, just because of the reason that if you take Le minus L mu and subtract a gauge charge, and then you think mod 3, then -2 is equal to 1. So there's actually a Z3 generation independent subgroup of lepton number that becomes non-invertible and disallows, say, Majorana masses for the neutrinos. And so we could follow our model building strategy and think about a UV model that introduces magnetic monopoles for L mu minus L tau, and that would have to generate from instantons these Majorana masses. Okay, and now we wrote down that model in the paper, but in fact, I think it's more interesting. Oh, that's the model building logic. Yes, we could do that. I wrote down that on paper, but I think in fact it's more interesting to go to the case where we have right-handed neutrinos as well. And in fact, again, there is a non-invertible symmetry. You just have to do more algebra to figure out exactly what it is, and I won't write it down. But again, the important part now is a Z3 subgroup, which is generation independent and gives the standard model leptons the normal lepton number charges, but gives right-hand neutrinos the opposite charge. And so now this non-invertible symmetry protects both Majorana and also Dirac masses. Okay, and now I want to follow our model building strategy and look for a theory with that introduces L mu minus L tau monopoles. Yes.
Sorry, just before we move on.
Yeah.
This N has charge +1. Why does it need to have charge +1? Why can't it be neutral under this new U1?
Why can't it be?
I agree with you that if N is charged under your U1
Yeah.
lepton number, then it's going to be charge 1. Or if it has charge 1, then that term is forbidden. But why can't it just be some fermion that's uncharged under all of my gauges?
Sure, if it's not a right-hand neutrino, right? Sorry. I should say these have the standard L mu minus L tau charges. So they're really leptons. If I were just to introduce some random fermions, singlet fermions, then they wouldn't take part in this anomaly.
Sure.
And so there wouldn't be anything interesting to say about them.
Okay.
Yeah, exactly. Good. And so once you have this guidance, and we want to look for a theory that introduces the L mu minus L tau monopoles, it's not so hard to think about exactly what sort of theory we should introduce. And the very nice thing to do, in fact, is to go to an SU3 horizontal non-Abelian gauge theory of leptons that just puts the 3 different generations of each of the types of leptons into the fundamental or anti-fundamental of SU3. Okay, SU3 has as a subgroup L mu minus L tau, and so this introduces the correct Polyakov monopoles of L mu minus L tau. And what that means is in this UV theory, what we can do is start in the far UV and only write down the charged lepton Yukawa, and everything, it's a flavor symmetry, so everything's flavor symmetric here. I've put the tau Yukawa as the largest Yukawa. And there's a classical symmetry that protects the Dirac neutrino mass term, but when I go coarse grain to the infrared, when I do some RG flow, in fact, there are these Toft vertices that in this case are relatively simple to understand. You have 2 L legs because of the SU2L quantum number, and one each of E and N. And from these vertices, you can insert a charged lepton Yukawa, and you get out a Dirac neutrino Yukawa, which comes from the charged lepton Yukawa, but is exponentially suppressed by the instant time action. Oh, good. And I forgot to give some spiel that you guys probably all know. If I chose to present the Dirac neutrino mass case because if neutrinos are Majorana, we know these lots of nice ways to naturally explain why the masses are so small, the seesaw mechanisms, I should say. But if they're Dirac, they have the same sort of masses as all of the other fermions. So then, to me, it seems like a big mystery why neutrinos could be so much smaller than the rest of all of the charged fermions. And to remind you of the hierarchy, between the heaviest charged lepton and the heaviest neutrino, it's about 10 to the 11th. Well, okay, we don't know exactly, something like that. So to me, it was quite amazing to find, and indeed, okay, people had, I should be careful with my words here, people certainly had written down nice theories of Dirac neutrino masses before, but often they contain, you need some, to add some complexity to your theory. To have some non-minimal ingredients. And here, this is really just a weakly coupled gauge theory in 4 dimensions of the standard model fermions, plus right-hand neutrinos, of course. So it amazed me, at least, to find that the standard model fermions sort of have in their power already to create this humongous hierarchy between the charged and neutral leptons. So that was rather amazing to me. I'll only say a few more words about actually the phenomenology because it's so relatively simple to introduce these. It's also very predictive. So if we go out and maybe tomorrow at the LHC or in some years at a muon collider, we discover a z prime for L mu minus L tau, and we measure its mass, which is like the range of the new force, and the gauge coupling, the strength of the new force, then in fact, we learn essentially the scale at which we should find the rest of the non-Abelian gauge bosons. This is a relation you can write down if we were to find a L mu minus L tau gauge boson at 1 TeV with a alpha of 1/20, then we learn that at 100 TeV, we should find the rest of the gauge bosons. And of course, really, I've only explained how we generate an overall exponentially small Dirac neutrino mass scale. I haven't said anything about the texture, which has to be implemented when you do this Higgsing from SU3 down through L mu minus L tau to nothing. In fact, Gonzalo Alonso Alvarez and Jim Klein understood how to do the right sort of Higgsing to get something realistic. And essentially this theory, although they didn't know about these instanton effects. Good. Okay. So now I'll turn to the quark sector, but I should pause for some questions.
Hey, coming back. So
yes.
your SU3 horizontal is a local gauge.
So it's a gauge symmetry.
It's you're spontaneously breaking it.
Yes.
To these globals.
No, sorry. So this is all.
L mu minus L tau is still a global.
No. That was a gauge symmetry.
It's a gauge.
That's right. Yes.
And then finally, you were spontaneously breaking that E1 L mu minus L tau as well.
Yeah. Well, we can't have it, unfortunately.
No, because people use two one, but you were using spontaneously.
Yes. Yeah. Eventually, and we were the topic of ongoing investigation. We only said a little bit about this in the paper, but indeed, you need to Higgs SU3 completely down to, well, maybe some remaining discrete factor, but all of the continuous gauge symmetry has to disappear. I agree. Cool. So let me go to the quark sector, after we wrote down this lepton model, I was convinced that there had to be something interesting to discover in the quark sector. Because, especially once you add right-handed neutrinos, there's like a structural parallelism in the standard model between the lepton and the quark sector. The quarks are essentially the leptons with color. And so I was convinced there had to be something else to discover. But in the quark sector, of course, we don't need exponentially small Yukawas, but there is another sort of very severe naturalness problem, and that's the strong CP problem. More severe and more subtle to understand, but let me try to briefly remind you. In the quark sector, there is this complex number M, which is field reaction invariant, which combines the determinant of the up and down quark Yukawas with the topological angle of SU3, that's theta. And the imaginary part of M is CP odd. It's a parameterized interval. It tells you how much CP violation there is in the strong theory of the quarks. And remarkably, we have found that the imaginary part is smaller than the real part of M by at least a factor of 10 to the minus 10. Normally people talk about this in terms of theta bar, the strong CP angle, but that's it turns out to be a bit confusing for the sort of thing I want to do. So if I'm talking about it in this way, we can chat about exactly why later. Anyway, okay, so that's already, I mean, this could be, you might expect naturally this to be an order 1 number. So already to say that it's 10 to the minus 10 is very odd. But in fact, it's even worse, as you probably know, because there is more CP violation that can take place in the quark sector for more than 2 generations. And for 3 generations exactly, there is one more CP violating parameter. It's this combination of the quarks, the commutator, and taking the determinant. And in this case, again, the imaginary part is CP odd, CP violating. And in this case, naturally, as you would expect, the CP violating part is the same order as the CP even part. It's an order 1 number. The CKM phase is a pi over 3 or something. And this is particularly problematic because now a small value of this strong CP violation is not even technically natural. If you go and look at renormalization group evolution, as you should expect, having 2 CP violating parameters in the theory of quarks, then the one that does run, of course, proportionally to the other. And so now, while, a small neutrino Yukawa is always an issue, at least they were technically natural, always, in the standard model. But this strong CP problem is not even technically natural. So it's a more severe sort of problem. And let me remind you that there was this one particularly beautiful idea for solving the strong CP problem that could have worked in the standard model itself. And that's this massless up-quark solution. Let me just remind you, in a toy model where we only think about 1 generation of quarks, and what you do here is in the UV, you impose what's called a Pechi-Quinn symmetry, say just a U1 symmetry that acts only on the right-handed up quark. And it's a Pechi-Quinn symmetry because this symmetry is anomalous. It has a mixed anomaly with QCD. So what happens? Well, you impose this symmetry, and that means that all you can write down in the UV is the down quark Yukawa, as well as this topological angle for QCD. And already at this stage, by computing that invariant on the previous slide, you can see there's no CP violation here, no CP violation allowed. You can make that a bit more explicit by using this anomalous symmetry, doing a field reduction definition of the right-handed up quarks that, because it's an anomalous symmetry, that shifts the theta angle, so you can use that to set the theta angle to 0, and just manifestly say, look, in the UV, all you have is this down quark Yukawa. There's no possible CP violation. Now, we actually know, of course, and have known for many decades, that the up quark in the far infrared has a non-zero mass. So you might ask, what in the world am I doing? But in fact, that's a feature of this solution. Because it's a Pechi-Quinn symmetry, an anomalous symmetry that's protecting the up quark mass, that means that as you slow down in energies, QCD instantons will violate this symmetry. And so the idea was, so QCD instantons indeed generate a mass for the up quark in the solution, very analogously to what we just saw in the lepton sector. but QCD instantons don't intrinsically violate CP themselves, and we started with the CP invariant theory, so you end up with a complex quark mass, but exactly no strong CP violation. This is a beautiful idea. Of course, in the actual standard model with 3 generations, there are many more legs on this Toute vertex, and also, as you know, the most important instantons are in the farthest infrared, and that's when QCD confines and becomes strong, and we lose analytic control. So the status of this theory, this idea, the massless subquark solution, had to be, well, was on ice for around 4 decades. But now some fantastic efforts by lattice physicists have unfortunately told us the standard model does actually not bear out this massless quark solution. Roughly, the QCD instantons are not powerful enough to account for all of the mass of the quark. But now we've just learned some new symmetry tool where we can understand when there might be new UV instantons that can do something interesting. So maybe there's a way to revive this model with some small instantons. And indeed, now let's think about analyzing the quark sector. You guys probably hear a lot here about these lepton family different symmetries, and people talk about them a lot. That's great, but we can think about exactly the analogous thing in the quark sector, engaging some flavored baryon. These are just more approximate in the infrared because the quark Yukawas are larger, but they're structurally parallel. We can think about gauging them. And in fact, in the quark sector, there's a more subtle way we can gauge this flavored baryon number because of this special mysterious fact that we have the same number of colors in QCD and generations of fermions, right? They're both 3. And so, in particular, we can gauge a combination like B1 plus B2 minus 2B3 or some cycle with, well, what's called some non-trivial global structure in the gauge group. Very roughly, we can talk about this more later if it's a novel idea to you, but very roughly, what this does is this identifies the Z3 subgroups of these 2 different theories. So it tells you if you go out, in fact, very far in make a large gauge transformation in QCD, very far from the origin. In fact, you end up in the flavor gauge group because of this identification. And that identification, what we're doing there is we're crucially changing the topological properties of the gauge group. Good. You can also think about upgrading the U1 like we did in the lepton sector into a non-Abelian SU3. And in fact, there's still some interesting global structure, which you could have maybe anticipated by saying, well, when I look at that non-Abelian flavor gauge theory in the quark sector, the quarks already had exactly this quantum number. And indeed, that's telling you that you can have this non-trivial option for the gauge group. And so, okay, there's a non-invertible symmetry analysis that you have to do here involving what's known as fractional instantons. When you have some non-trivial global structure, you can have instantons actually with fractional quantum numbers that can only exist really on spaces of non-trivial topology, just like the actual U1 instantons can only exist on spaces of non-trivial topology. They're not there in R4. And that's exactly the sort of thing we want to find a non-invertible symmetry. You have to do a slightly more careful analysis. In this case, I won't go through it, but we can talk about it, or it's in the paper. You have to think about which symmetries have mixed anomalies in integer instanton backgrounds. Those are just broken. Those can be realized on R4. But if they only have a mixed anomaly in fractional instantons backgrounds, again, they have an anomaly formally, but that instanton isn't realized on R4, then those symmetries become non-invertible. And in fact, what eventually the important part of the non-invertible symmetry that you find is exactly analogous to the lepton sector. There's a generation-independent Z3, which looks like baryon number for Q and U, but gives down quarks the wrong sign charge. And so all of the down Yukawas are now a spurion for this sort of non-invertible symmetry. And again, we can follow our same model building logic. we have a global symmetry, it protects some operator we care about. Some, it has an anomaly, but some of the instanton numbers are not available on R4. So we have a non-invertible symmetry, and we should think as model builders about going to a UV theory that introduces the correct monopoles. And indeed, what that leads you, in this case, is to a beautiful theory of color flavor unification. In fact, this theory has seen essentially no study, but in fact, you can put the 3 generations and 3 colors of each sort of quark into the fundamental of an SU9 color flavor unified theory. And you can do exactly now a flavor symmetric massless quark theory, where you start in the UV with a Pechiquin symmetry acting on the down quarks. You only write down the up type quark Yukawa. The top is the largest, so I put that there. Again, there's no CP violation to begin with. And then as you flow down, we have, again, these instantons, which generate toast vertices that can generate for you a down type quark Yukawa, now a bottom Yukawa, the largest one, but while preserving strong CP. Indeed, in these theories, we can revive the massless quark solution using some now flavor symmetric UV instantons. And there's a nice fact that actually these, the theory SU3 squared mod Z3 is sort of non-trivially embedded in some interesting wrapped way in this SU9. And that means that as you go to the UV, in fact, the gauge coupling jumps and becomes automatically a factor of 3 stronger. And so there's a good reason that these UV instantons are stronger and can make up for some of the deficiencies of the standard model instantons. Now, I'm running out of time. I haven't, you should all complain because actually in this theory, there's no other CP violation in here. When you have the flavor symmetry, there's no CKM phase. So in some sense, this is so far just a trivial solution of the strong CP problem. But in fact, there's a very nice way that you can generate, at least in principle, we showed the full flavor structure and required CP violation in the Yukawas, in the CKM, while not upsetting this solution. You can use the gauged flavor symmetry to communicate flavor breaking and CP breaking from the VEV of some scalar field that can't directly talk to the standard model fermions at tree level. And what do I want to say here in a minute? Well, good. So this scalar that's getting a VEV has some CP violating terms in its potential. These are complex. But what you can notice is in any diagram you write down that communicates the flavor violation and CP violation from the scalar to the standard model fermions, whenever you have a diagram that has, say, this CP violating parameter inserted on the sigma line, there's a Hermitian conjugate diagram with the Hermitian conjugate vertex inserted on sigma dagger. And so you generate general complex matrices, but they are always in fact Hermitian. And so this determinant of the product of the Yukawas is automatically real, although you can in principle get a general CP violation and flavor violation there. Okay, there's more for me to say, but I'm running out of time, so I can save this for lunch or when you want to talk to me later. Let me give you my conclusions because it's 2024 and you have to back yourself. I think any place that non-perturbative effects might be phenomenologically relevant, this paradigm that we're learning about of more subtle generalized global symmetries, I think might offer some better understanding. So there's lots of things to think about. I'm quite amazed that already with this, with quite simple uses thereof, I've located some new unified theories where instanton effects only with the standard model fermions can possibly solve some standard model naturalness issues. And I think this means that as particle physicists, we are not yet done learning about the role of symmetries in our theories, and I look forward to doing so further. Thanks very much for your time. sorry to rush there at the end. Oh, yeah.
Yeah, please. Any questions?
So naive bottom-up perspective on the shrunk CP solution. From the bottom up, I think of this as just there's some new symmetry that is forbidding my down quark term, at least at tree level, and then it's
In the
generated.
far UV, yes,
Yeah.
and then it's generated by this. That's right.
So we know that the Higgs has Yukawa couplings to the in the IR has Yukawa couplings to the non-type quarks, at least to BB bar that we went that at LHC. Would the positive measurement of Higgs to SS bar and DD bar at their expected strengths, according to the standard model, just with those standard Yukawas, would any observation of that shed light on what you're showing, or is that all consistent with this small instanton generated?
Yeah, no, that's all consistent, but by the time we get to standard model scales, it just looks like the Yukawa couplings that we're familiar with.
So other than figuring out the scale of this symmetry breaking and maybe finding the new bosons associated with that, are there any other clues that we would get to unravel this?
Yeah, so it's a good question. To some extent, these the theories are suffering from success, and that we've introduced quite a few moving parts. Indeed, so far with this, it's hard to see really a low energy probe. Something to think about, which we are thinking about and definitely needs a lot more thought, is what effects there might be in early universe cosmology. You know, you're introducing types of topological defects that interact directly with the standard model fermion. And so there may be interesting signatures there in gravitational waves or something more subtle. But also it would be interesting to include more in these theories flavored dark matter or some other modules, which is a standard model building sort of game, some other ingredients that can do more, but also maybe have more visible effects in the infrared. Yeah, that's a good thing to call attention.
Sure. So since you have a flavor symmetry you have introduced, maybe your axion coupling in the visible sector could be different compared to KSVZ or DFS.
Well, I don't want to introduce an axiom, right? Because I'm here.
At the end, there will be a U. That's your you want picture. So
No, this is a massless up-quark solution. So
so
there's
you
no
know
axiom.
axiom.
That's right. Now, okay. Now, it's a good question. Actually, you're right that an axion version of this theory, I think, has some interesting features, and we're currently exploring that. Indeed, I think this can provide a model of a heavy QCD axiom in that direction. Although that's not a feature of this model that I'm talking about. But you're right. That's another good idea and something that we're looking into.
So in this, like, when I think it was asked before, so, but like, if I have to think of like an early universe or anything, I would need to write down some counter. Because we wrote down like a partial mu, J mu, and like that was like the basis of like equal to 0. But then if I simply promote it to the covariant derivative, will that do the trick, or do I need to do something else in order to like incorporate and like suppose I do the calculation effort?
Yeah, I think upgrading that to a gravitational covariant derivative is the only effect there. I mean, not so much in I don't think so much like affecting one of the equations I wrote down, but more that I talked about these types of monopoles that will exist in these theories. We talked very briefly about these types of monopoles that will exist in this theory, or even in, remarkably, for all of the hundreds of papers that have been on L mu minus L tau as a gauge theory, there's, to my understanding, been essentially no work on L mu minus L tau monopoles, right? Which should be a feature, just like we think monopoles of the standard model U1 factor should be a feature of the early universe. Monopoles of L mu minus L tau should be a feature of the early universe. And these are very interesting because, well, A, they interact strongly with all of the standard model leptons, and B, you don't have the monopole problem that you have for really electromagnetic monopoles, because when you break L mu minus L tau, they disappear, they annihilate automatically. So those sorts of monopoles could really be around in the post-inflationary plasma doing things. I don't know exactly what, and it would be very interesting to understand what signatures they have. And in the quark sector, there's an analogous thing. It's a bit more subtle because they're in fact discrete magnetic monopoles. But yeah, that's sort of what I was alluding to, actually thinking about when you have these topological defects in these sectors on shell in the early universe, what sort of interesting effects might there be? And I don't have a good answer for you.
Also, if you introduce really at the end non-renormalizable, those could be still there, and they can introduce these small effects. Then how would this really you will end up seeing this global symmetry? Because at the end, gravity induced effects could be there, like a global symmetry.
Well, we're generating marginal operations, right? The Yukawas.
Right.
So that sort of makes sense why they can have end up producing the Yukawas of the standard model. Yeah, looking for
tiny global symmetry breaking operators.
Yeah, sure. I mean, and of course, you're right. As you started the talk off asking about, you expect a theory of quantum gravity will introduce that. That doesn't affect the quality of these solutions. In fact, they're robust to the addition of quantum gravitational breaking of these symmetries. I should have said
for
that.
example, E-quark mass or D-quark mass, cannot I just introduce a tiny little effect that can come from also non-renormalizable? Wouldn't this solution then?
Yeah, good. So there is something to think about and calculate here. And oh, I have too many backup slides, and I don't know that I'm going to be able to find the right one. Oh, well, that's not the right thing to do. So in fact, you're totally right that there is a here we go. Fine, good. Here we are. Good. So you should think about quality, but in fact, the quality issue in the massless up quark solution, how do I make this larger? The quality issue in the massless up quark solution is much better than in the axion solution. For a couple different reasons. Well, really, the main thing is that in the axion solution, you need to care about the potential, a dimension 4 contribution. And so indeed, that makes the axion very susceptible to some modification here. But because in the massless up quark solution, the comparison is in the Yukawa, is in that coefficient. In fact, it's much simpler. You're right that now I've introduced some scalar. I should write down like a dimension 5 quantum gravity generated term. But as long as the flavor breaking scale is not too high, that's totally fine. So in fact, quantum gravity in this case would motivate that flavor breaking should be around 10 to the 8 GeV or something. Which is, that's useful as model is to not have flavor breaking too far off, but maybe somewhat visible. So yeah, definitely it's an important thing to think about, but actually that's a place where the massless quark solution wins compared to the axion solutions, which is an interesting effect. Maybe I should put that in the main talk.
Also, by the way, the Hermitian Eucos with this correct CKM, actually it can be obtained.
Right, it's a feature of parity solutions. That's right. Yeah, so it would be very interesting to understand if there is some deep relation in how we're finding that coming out here to parity invariant solutions. I don't know the answer.
That's the part which was kind of making me a little bit curious about your solution, because parity invariant solution right from the beginning, if you take the axiom from the
yes,
right?
Yes,
and so we try to do them.
Yes.
Physics.
Right.
That time we realized that parity, like a Hermitian equals can give us.
Yes.
But how do you end up in that solution using some horizontal symmetry? That's a curious.
Yeah, so I think it's and good. I'll admit that I don't understand. I think we showed that in principle it can work. I don't understand it.
You get the parity.
So, well, it's not really parity, but it's a feature of how we communicate the flavor breaking to the standard model quarks. I don't think it is that there's a parity.
It has to be.
Yeah, good. Just because for every diagram that you can draw, that has some flavor breaking, some CP breaking, there's always a Hermitian conjugate diagram that only Hermitian conjugates the scalar sector.
But didn't you assume some spontaneously broken piece which can have a complex wave in?
Yeah, indeed. So here it's even explicit. Here I'm saying even explicit CP violation works. So I've written down. Sorry. So I should be clear. Sigma is two adjoints of SU3 that I've combined into a complex adjoint. Sigma 1 plus I sigma 2. And indeed, I'm writing down at least some of the explicit CP violating terms in the potential that you can get. Sigma is going to get a Vev and spontaneously break the flavor symmetry and also communicate this CP violation.
Maybe parameters you chose them to be real. Your
Nope.
Gibbs parameters are.
No, it's entirely general. But the point is, indeed, there's some complex parameter here that has CP violation in it, sure. But there's always I can put the Hermitian conjugate of that operator, I can insert it on the Hermitian conjugate leg. So for whatever diagram you have that introduces flavor and CP violation from the scalar sector to the quarks, there's always a conjugate diagram that gives exactly the Hermitian conjugate contribution. So you end up with complex Euclides, but automatically Hermitian conjugate. Sorry, Hermitian, that is. I should say I won't be offended if anyone runs out of here. I mean, you have lives to lead yourselves, so don't worry. We can continue talking. Yeah, but no, I agree. We don't understand this fully. We're confident that it works in the way we say, but it would be good to understand the structure of what's happening here better, more.
Because for supersymmetry, you have to assume that new parameter has to be real.
Right.
Somehow we did it.
Yeah.
And otherwise we could not keep the parity preserving symmetry. But
Yeah.
here you are keeping the parity preserving.
Well, so again, it's not parity. I mean, I haven't.
But at the end, they could show up.
Yes. Well, sort of. Yeah. I'll say, I mean, my feeling for having thought about this for a long while is that vector-like fermions are actually really dangerous for theories of strong CP, right? I mean, when you have vector-like fermions around, it allows for a proliferation of CP phases. And so this theory does not introduce any vector-like fermions. We're only communicating flavor and CP violation through the gauge interactions, more or less. There's a caveat, but I think somehow that feature, not having any vector-like fermions, is letting things work more smoothly than they would in some general theory that includes them. But it's a good question. I'd like to understand better. Cool. Great. Thank you all.
Any other questions?
Oh yeah.
Let's thank the speaker.
Thank you. Wait. Oh yeah. Somebody has to stop the recording. Do I stop the recording?
Reading the host.
Oh. Okay. Perfect.